All right, guys, today we're going to learn a little bit more in depth, or at least get it in your notebook, about deep ocean currents. So you have this already glued in your notebook, and you're going to fill this out as we watch this video. So deep ocean currents are driven by differences in density. So surface currents that we talked about were the flows of water on the top 100 meters of the ocean water, and they are driven by wind. And these are deep ocean currents, currents that flow way down deep in the ocean, and what causes them is differences in density of the water. One thing that affects the density of water is temperature. And the higher, we've learned this earlier in the year, the higher the temperature of a liquid, since we're talking about the ocean water, the more the particles are moving around. So if something has a higher temperature, that means that the thermal energy is increased in that substance, and the particles are moving all around faster, they're spreading apart from each other. When particles start to spread apart, that means if you're talking about the density of a certain area, there's less matter in that space, and therefore that part of the water has less density. Once it gets colder, though, those particles start to slow down, and they enter into that space where originally there wasn't as much particles. And so now we have more particles crammed into that space, and so therefore it's denser water. The second factor that affects the density of water is salinity. Salinity is the salt content, so make sure you know that salinity is just the amount of salt in the water. And so the less salt content, that means the less denser the water, the more salt content there is within a certain space of the water, that means the more dense it is. It's all about how much matter is crammed into amount of space. So the next thing that you have on your paper is to describe the process of thermohaline circulation. And if you look back up here, you'll notice that beside temperature, one of the factors for density changes is the word thermo. And that's because thermo is related to the word temperature. And haline, I don't know if you remember me talking to you the other day, haline is also up here beside salinity. The mineral halite is natural salt, and so the word haline usually refers to salt. And so when you put these two words together, we're talking about how temperature and how salt create circulation of the water between surface and deep ocean currents. So when I ask you the process of thermohaline circulation, all I'm asking you to tell me is that surface water may become more dense and go deeper in the ocean because it has either gotten colder, or it gained more salt content, or a combination of both. Now, this process of thermohaline circulation forms the global conveyor belt. And I want you to think about what a conveyor belt is. And all a conveyor belt, like if you think of them in real life, so sometimes on those big trucks, construction work, they have like this belt that goes around the tire. Or when you're in the grocery store, there's that conveyor belt that goes, brings your groceries up to the clerk, and it's just a conveyor belt that moves your groceries. So when you think about what a conveyor belt is in our own daily lives, think about the ocean water now. Every time that the surface currents flow and become more dense and then drop to a deep ocean current, that is part of a conveyor belt moving that water from surface to deep. And then it can come up to the surface again, which we'll talk about later how that really happens. But that is the conveyor belt of that water, circulating the water from surface to deep and back to surface again. All right, so the whole awesome thing about ocean currents is that it helps spread the heat that's mainly at the equator all throughout the globe. So we don't have an extremely, extremely frigid place on our planet, and we don't have an extremely, extremely hot place on our planet. Those ocean currents help to kind of moderate all the temperatures globally, spreads the heat around the globe. I do want to go back for 1 second and show you this. quick video. Okay, here in the video, you can see that they made cold water blue and hot water red. And then they covered them with foil. And they kind of put just a hole in the top, a little pencil sized hole. Now they're going to turn those over. And I want you to make some observations about where the red warm water goes and where the blue cold water goes for a second. So you can really tell here that the blue cold water must be more dense because it is sinking in the regular room temperature water. And the red warm water is rising, so it must be less dense than the fish tank water, which is just at room temperature. So that's just an example of how temperature can play effect in the density of water. All right, we're going to go back to this presentation. Okay. All right, so moving on. We're going to talk a little bit about this global conveyor belt, and as we talk about it, we're going to add things to the map right here on your paper. So a couple of things that we want to make sure that we include is this first thing. There's no starting point of the conveyor belt that moves this water, but I like to think about the Gulf Stream as it travels north between northern Europe and Iceland. The Gulf Stream water becomes more dense, and it's because it's getting colder and it's also getting saltier. And we're going to talk about why it gets salty in a minute, but the first thing I want you to do is make sure that you circle this area right here where you see the Gulf Stream, the warm water flowing up. I want you to circle it where it curves and goes into cold water. And this is where the Gulf Stream becomes more dense. Write that out here. Due to being colder and saltier. Now, why does that happen? All right, so and I think we talked about this a couple weeks ago, but when water freezes, the crystals like push out the solid particles. So it's the liquid, the water, turning into solid particles. The salt that's dissolved in the ocean is already a solid particle. It's just tiny little pieces of it instead of bigger chunks of it. And so it basically just gets pushed out of between the water molecules. So when you see frozen things in the ocean, whether it be like sea ice or whatever, those are actually fresh water. And we talked about that. We said 2% of the fresh water, or 2% of the water on Earth is fresh but frozen. And so that's how this happens. But here in this diagram, I just kind of like this diagram right here. It does show us, and this explanation is great. It says thermohaline circulation begins in the Earth's polar region. So we're talking about way over here, where the Gulf Stream goes up between Iceland and northern Europe. That would be one area. The ocean water in these areas gets very cold because of the indirect light almost year-round, but particularly during the winter time up there. And sea ice forms. So this is just a chunk of ice that is forming in the ocean. It's not connected to any land form. And the surrounding seawater, because that is freezing up the colder it gets, the surrounding water around that sea ice becomes saltier and saltier and saltier because the salt is being pushed out. So just wanted to have you kind of see that. I think it might help you understand how the Gulf Stream becomes more dense when that sea ice starts to form way up near the 60 degree to 70 degree latitude line. All right, so some of this we're not going to include on here, but basically that water sinks. It and on top, so this, it collects all that salt and gets colder. It sinks, but in to replace it, right behind it is more salt water, so it keeps that water flowing. And again, that's that high pressure to low pressure phenomenon that we've talked about several times this year. And that sunken water just kind of moves along the sea floor. It does come back underneath the Gulf Stream, deep down in the ocean. It makes its way towards Antarctica and then funnels around. You see part of it goes to the Indian Ocean and part of it goes to the Pacific Ocean. So, if you notice, this deep ocean current turns back into a surface current, both in the Indian Ocean and in the Pacific Ocean. And the reason for this is upwelling. So what I would like you to do is to circle these two loops, both in the Indian and the Pacific, and write down here that deep ocean water is turning back into surface water due to upwelling. And here we're just going to talk about what upwelling is. It is because that deep ocean current has come to an area where the continent is in the way, and there is very shallow ocean water compared to other areas. And so what's happening is that continent is allowing that water to get pushed up higher into the ocean. And this can be really awesome as far as replacing some of the nutrients in the water where we might fish or where we might be exploring the ocean or whatever. So it allows for that dense, cold water to be pushed back up due to continents blocking the path of the ocean current. All right, so moving on, it's important to know that the deep ocean currents actually move a lot slower than the surface currents, and there's some measurements there for you to check out. And lastly, about deep ocean currents is that a couple days ago or a week ago, you were a water molecule. And water molecules form water droplets when in the ocean. So if you're thinking about a water drop in the ocean, it would take you about 1,000 years to travel around the entire global belt and make your journey from start to finish. So that's kind of cool. Little fun fact is that it's about 1,000 years. Now, there's a video linked in the Blackboard page that I would like you to check out. And it will recap basically everything I've said, just in a different way. And so sometimes hearing that information can be beneficial. So please go to Blackboard and click on this recap link, and it will take you to a short 4 or 5 minute video about the global conveyor belt. Here's a different diagram, and I don't know that we need to talk about anything specific here. It's similar to the one that you have on your paper. It does have the two tones so you can kind of see the surface and the deep a little bit easier. The last major fact that I need to talk to you about, and you might have already filled in some of it at the bottom of your paper, but it says, how does water become more dense when it freezes? Well, earlier we talked about when it freezes, the ice crystals push out those little tiny solid salt particles. So it is the liquid that is freezing into a solid, but the salt is already in solid form. The evaporation process. So evaporation, when the liquid is turning into a gas, it's gaining thermal energy, turning into that gas, it is leaving behind the solid particles. Solid particles normally don't just skip from solid to gas. So a solid particle would have to melt into a liquid and then evaporate into gas. So a lot of times when water evaporates, it's pretty clean. It is part of the purification process within the water cycle. One area on Earth that's pretty interesting to know about is the Mediterranean Sea. It is a very, very dense area, and we put this on your map the first day we took ocean current notes. And the reason was I just wanted you to know where it is. It's located between Africa and Europe, and it is a very dense area, and it is because there's lots of evaporation going on, and therefore there's lots and lots of salt content in that water. So what you have going on is right here at the Strait of Gibraltar, we have a surface current flowing in that does not have much salt content in it, and is pretty warm, and so it's not very dense. And then in here is where a lot of evaporation takes place, and therefore we have a deep ocean current flowing right back out the Strait of Gibraltar. So when